Thank you for the introduction, Manfred. I'm Taro Saito, an engineer from Treasure Data, and I'm going to talk about Secure Exchange SQL, which is a privacy-preserving data clean room built over Trino. So let's get started. Okay, so let me introduce a brief history of Treasure Data. I can't tell the history of Treasure Data without Trino. Treasure Data was initially founded in 2011 as a Hadoop as a service company in Mountain View, California. Then, while we are operating query engine as a service based on Hive, we were looking for more interactive query engine services. Then, in 2013, Presto was open source from Facebook. So we immediately jumped in the opportunity, and Treasure Data quickly launched Presto as a service in 2014 for providing interactive query processing as a service. Then many users started using Presto on our services. Then 20,000 queries are processed every day in 2015. Then in 2019, the number of queries reached 1 million queries every day. At that time, we also organized Presto Conference Tokyo in Japan by inviting 3 Presto creators, Martin, Dane, David. You can find the blog post about this conference in Trino blog. Then, as you know, in 2020, Presto was rebranded to Trino. Then our Presto and Trino usage has increased over years. We are now processing over 2.5 million queries every day using Trino. Then in this talk, I'm going to introduce about our data clean room service, which is called Secure Exchange SQL internally, which is built based on Trino. Then here is the basic architecture of Treasure Data. Treasure Data has 2 types of data collector system. Fluently and Bug. Fluently is open source streaming ingestion library so that you can ingest data to anywhere. Or Mbug is a bulk data import system. You can connect to arbitrary systems to JDBC or some APIs. Then you can ingest your data into our storage. We have 2 types of storage: real-time storage, archive storage. Archive storage is more performant storage types. So the real-time usually has fragmented partitions. So we are going periodically merge fragmented S3 files into archive storage. Then to make query processing more efficient, we are building partition indexes over Postgres and over S3 objects. We are also managing our own table catalog. So our index is maintained in Postgres, so transaction can be naturally supported over years. So recently, community is catching up. Data lake, Iceberg support for managing transactional update table, but we've been managing transaction over years based on Plasma DB system. And our customers can run Trino or Hive queries against the system. Then as you run a query, the query logs will be collected by using our own system. So surprisingly, we have been collecting over 10 years of query logs by using our own system. That makes possible to keep operating Trino for over almost 10 years. Then, so by using query logs on our system, we can build customer-specific benchmark. So before doing any upgrade of Trino, we can run pre-production simulation custom queries by using real data. Then we can report the difference between Trino versions in terms of performance or query syntax compatibility. Everything can be checked before making it production system. So for more details can be found in our DB test workshop paper, Journey of Migrating Millions of Queries on the Cloud. So check it out if you're interested. Then the Trino usage of Treasure Data in 2023, we now have 700 accounts, 6,000 Trino users in our system. The usage has increased almost 2 times since 2022. We are now processing 2.5 million queries every day. User is processing more than 100,000 queries every day. The number of loads processed is exceeding over 200 trillion rows every day. In terms of S3 GET request counts, we are issuing a lot of 10 billion S3 GET requests every day for reading partition data stored on S3. So Treasure data has a lot of Trino usage. Our customers using Treasure data as a customer data platform, CDP, so that they can collect their own customers' user activity logs on CDP. So our current challenge right now is how we can facilitate sharing data between CDPs while preserving privacy. So this kind of system is usually called data clean room or cross-party data sharing. So let's look at what we implemented in this context. So Secure Exchange SQL is a brand new service on Treasure Data CDP, which enables privacy-preserving cross-party query processing using Trino. So basically, we have two players, consumer and provider. Provider usually has big volumes of data from a lot of user base. So they want to share the data, but they don't want to share raw data directly to consumer. So provider usually want to share only aggregated statistics to consumer. The consumer usually don't have so many data by themselves. So they want to enrich their own data by using other big data providers' data set. So Secure Exchange SQL is try to bridge those two parties by providing privacy-preserving database engines over Trino. So basically, yeah, providers have their own database, consumer has their own database, but query runs inside the provider's account so that then consumer need to provide their access delegation token to Secure Exchange so that the provider can access consumer's table to take a join between multiple parties' data. But consumer only see anonymized statistics so that, yeah, in order to protect the privacy of provider's data set. So that's the overview of Secure Exchange SQL. Then internally, so given a SQL query like disaggregation, which is reading data from access logs and grouping by some advertisement campaign, then counting how many users click the advertisement. So this query needs to be anonymized to protect the privacy. In order to do so, we are going to add some noise to the count and also adding some grouping threshold to hide wizard from a small number of people, like less than 100 users. Data need to be excluded from the query wizard. Then to adjust the privacy protection level, we are going to change the epsilon parameter following Laplace distribution. So this is an overview of how we are going to rewrite SQL query. This is where it happens internally in our system. Then the notion of differential privacy comes into place, which is a method for quantifying the privacy by using epsilon parameter. So as you can find in this chart, if you use higher epsilon value, it adds less noise. So the data will be close to the original value, but it also means user loses more privacy. But if you use lower epsilon value like 0.25, more noise will be added in the broad shape of Laplace distribution. So it protects more privacy because query wizard will be randomized a lot. So in the context of this differential privacy, epsilon parameter is called privacy budget, which means if you run a query against the data, you will consume epsilon privacy budget for the database. Then once the entire budget is totally consumed, no more query can be issued to the database. So which is the basic concept of differential privacy. And actually, you have seen the real example of application of differential privacy. For example, Google Maps provides a visitor histogram of the restaurant or stores. If you visit some restaurant, then histogram will be updated. But actually, Google Map adds a noise to the histogram to randomize the results. because if no noise is applied to the histogram, once you visit some restaurant, then histogram will be updated like this. So it actually leaks some privacy of your data. So Google is taking it very seriously. So they are trying to make almost any types of analysis some privacy protection by default. If you are interested, you can find their communication ACM article. Yeah, it's very interesting read. Then here is some internals of Secure Exchange SQL, which is actually an SQL compiler written in Scala programming language, which is using the same anti-error for grammar with Trino SQL. The first step is passing raw SQL statement like this, select something from goodbye. Then by passing this SQL statement, it generates a logical plan structure like this. But this logical plan doesn't contain any table schema or personal data information. So we need to populate this logical plan by using schema information from the table. Then after resolving all column types or column names in all of the logical plan nodes, you can find how personal data is propagated from the input table to the output table, output result. So in this example, from a table A, ID data will be exported as a query result. So tracking the propagation of personal records is really essential part of Secure Exchange SQL. You can find implementation of this SQL module as an open source in Airframe SQL module. But other part of Secure Exchange is, unfortunately, it's a private closed source round. Then the next step is validating SQL plans by traversing logical plans. So we need to reject certain types of queries like update query, DDS statements, because we only provide aggregated query statistics. Then this rule is trying to reject other non-relational queries. And also this rule is traversing SQL statement. If private column is used for output columns, then it will going to reject the query. So it leverages a powerful pattern matching capability of Scala. The next step is rewriting SQL in order to transform logical plans. As, for example, we can add noise, or we can add thresholding condition for group by queries. This one is a bit complex to read, but basically this part is trying to find aggregation expression inside the logical plan. Then if we found some aggregation expression, then we are going to add noise UDF here for count, approx distinct country. Those are variations of count queries. After rewriting query, we need to validate query again by using some various validation rules to ensure the rewritten queries are following privacy policies we implemented. The final step is just generating a plain SQL statement which is compatible with Trino so that we can run the query by using Trino. That's our overview. Then rewriting part can be really complex. So this one is really complex. It's one of the complex examples in our rules. Just adding having condition to add the threshold. We need to write this kind of rule. So this one is trying to find aggregation node and adding threshold condition here. But for adding threshold like count distinct against personal identifier, we need to be able to find personal identifier from subqueries. So if subquery is not explicitly written in the query plan, we need to pull up a personal identifier column from table scan level or bottom of the subqueries. So this kind of reality is happening in these rules. So the challenge was testing how source query rewrite is actually correctly working or not. To simplify the testing process, we've implemented a simple testing framework. query spec is written in YAML file. Original SQL, the rewritten SQL expected rewrite of SQL is inside the same YAML file. We can add more configuration parameters or table catalogs in the same folder. Then we can verify query rewrite result by using those test cases. We have a whole bunch of test of YAML files in our test cases. Then to quickly test those rewrites in unit test level, we are locally launching Trino inside the unit test, then actually execute the query in Trino, then verify whether we have any syntax errors or not. In Security Exchange, we supported only limited subset of Trino SQL. Basically, we only support select group by type of queries. No update is allowed. Basically, query statement need to have an aggregation. Only aggregation results can be used in the query statement. So every query must have count, some averages, and so on. Some aggregation function like array arg window function might involve personal records inside the query wizard, so we can't allow using those functions. And also, yeah, we need to make sure no private comments is exposed through group by keys or final output projections. You also need to make sure personal records will not be amplified by using joins. Right? So we only support equal join, which is inner joins between personal identifiers using equal conditions on PID. Then why do we need to restrict the query types on the aggregation queries? This is mostly for avoiding direct share of low personal records, which is really good for taking user consent. We are managing personal data, so we need to get an agreement from user to use the data. But most of the users don't agree for directly sharing their personal data to other parties. So what companies can do is sharing only anonymized statistics. And also, yeah, this is also good for being compliant with various privacy regulation laws like GDPR, CCPA, HIPAA. Those require some control access to private data, and those are not allowing directly sharing low personal data. Also, you might have seen various access control methods like database table, common label permission, or common value mask using Apache Ranger, which is also supported in Trino as a plugin. Then you might find hiding name or SSN, social security number, can work for protecting the privacy, but usually those are not sufficient. Even though private comments are hidden, other non-private comments like zip code, birthday, sex can form a quasi-identifier. Then you can identify personal information just by using non-private data. Actually, 87% of US population data can be uniquely identified by using the birth, sex combination, which is really surprising. Additionally, only sharing aggregation data also has a risk of privacy leak. So here is aggregated counts of US population data. This one is a very small example. 7 people in the database, median age of those people 30, or mean age is 38. Yeah, only sharing those aggregated statistics might reveal privacy because we can create rules for producing those query results. We populate original data with some variables. Then we can create a lot of constraints. Then in this table, we can form 164 constraints. By having these constraints, we can use some kind of brute force attack. Then we can use SAT solver. Then we can totally reconstruct the original data in 0.2 seconds. So sharing aggregation data need to be very careful and probably need to be managed. So here is Differentially Private SQL engine. So Differential privacy itself was a theory formalized by Sincere Dirac in 2006. to provide a mathematically rigorous definition of privacy. The DB itself is a property of mechanism. In this context, it's a SQL engine to produce almost the same query result, regardless of the presence or absence of a single person in the database. So differential private SQL engine need to consider all neighbor database in which some individual's data might be missing. Then by applying some magic, the query result should be almost the same. This is actually implemented just by adding some noise to the query result or adding some grouping threshold. But the core concept of differential privacy is query result need to be almost the same regardless of the presence of any individual in the database. Then you need to take care of aggregation query to make it differentially private. Group by might produce really unique key values if from a single individual. For example, in this case, some unique group by key can be produced. If that kind of data, in that kind of data, query against database 1 and database 2 always produce slightly different query result. So it is not differential private at all. To make this differential private, we need to make sure those small values will not be exposed in the query result by applying some grouping threshold like this. So by cutting off some small data coming from small number of people, we need to apply having count distinct threshold. Another challenge is we need to think about the sensitivity, which means how sensitive the query result is against presence of a single person in the database. For example, if a single user has 1,000 of records in the database, the result of count query can be changed by 1,000 if user is removed from the database. So depending on how many records you have in the database, the sensitivity of the query will be changed. So if sensitivity is really high, you need to add more noise to satisfy differential privacy. A practical approach for addressing this issue is taking at most k records from each user by sampling, which is implemented as a window function in Trino by using a memory-efficient reservoir sampling method. You can find more details. A reservoir sampling itself is a well-known algorithm. Then we are going to keep adding new rules for making sure the query result is almost the same, regardless of the presence of any individual in the database. So we accumulated rules. And we have 30 more rules for validation, SQL rewrite, for adding noise threshold or user contribution bound, and so on. And those rules are a bit configurable by using feature flag. Sometimes we can turn off some of the rules. Those are actually leveraging the powerful pattern matching in Scala, which requires recursive tree traversals and transformation of logical plans. You can find similar example in Spark SQL, which also uses pattern matching of Scala for optimizing queries. We are now seeing increased adoption of differential privacy. The 2020 version of the US Census data is published with noise that has DB guarantee. Google also open source some part of the library for adding noise, or Data SQL, which is a query parser using BigQuery, also has a DB SQL support. Google also use the differential privacy for COVID-19 tracing data. Then you can find more detail in their CACM article. AWS just announced differential privacy support in their AWS data clean room last month. So we are seeing more and more adoption of data clean room. So here's a summary of the Secure Exchange, which is a differentially private SQL engine that produces almost the same query result regardless of presence of an individual in the database. The good thing about Secure Exchange SQL is it has built-in privacy protection. So it tracks how personal records are propagating inside the SQL statement. then adding necessary anonymization by noise or thresholding or sampling if necessary. Now, actually, this implementation is minimizing changes to Trino itself. So writing SQL happens outside Trino. We only need a couple of UDS for adding noise or sampling by your window functions. Table catalog is, we've been using our own table catalog almost for 10 years, so there has no difficulty for us to implementing access delegation to another account. So yeah, that's a summary of this talk. Then there are a lot of topics that cannot be covered in this presentation, like sensitivity for other aggregation data, how to manage privacy budget, using different types of noise, like Gaussian noise other than Laplace noise, or how to apply differential privacy to machine learning. So those topics you can find related papers, books, article in this link, readings in differential privacy. This is a curated list I've been managing for keep learning about differential privacy. Okay, so I'd like to thank many people, many colleagues in Treasure Data by using this place. So those people, mostly engineering, but product managers, the sales people joined to this project to make it possible. Thank you them all, and as well as Trino community members as well. Without Trino, this project could not be materialized in reality. Thank you guys. That's the end of my presentation.
Thank you very much for the presentation. That was really interesting and engaging talk. We do have one question in chat, if you're willing to answer that, about what happens if you're interested in long tail results. Because using this method, it seems like those might be hard to track down.
Yeah, so actually differential privacy is basically can be used for tracking large population of results, for example, more than 100 users or 1,000 users activity can be tracked, but it's not good for tracking really small number of groups of people. Yeah, so probably basically we need to give up long tail analysis of long tail people populations. But there are several techniques like applying user level aggregation in advance, then trying to create a summary of small group statistics. Then you may be able to find some insight even from small groups of people. But differential privacy is not usually good for tracking small number of people's activities. So basic approach is give up differential privacy and use different approach, for example, only allowing specific type of SQL queries that is verified manually by human eyes. If providers agree to run this query, you can run this kind of analysis. So that kind of arrangement is necessary.
Thank you for that answer. If anyone else in chat has questions, we do have a few more minutes. We can burn on Q&A. We'll see if anything pops up. Perhaps not, in which case I may just introduce the next session. I'll give it another moment or two. Sometimes people need to think a little bit to formulate their questions. They're like, "Oh, hold on, I can ask a question. Let me rack my brain for what I want to learn." Don't be shy, everyone.
It's actually pretty new topic, so I needed a lot of time for catching up with understanding what is differential privacy. So I try to extract really an essence. So probably key takeaway is this one, only this one. So differential private SQL engine is producing almost the same query result, even if your database has missing some individual So that is the key part. So you don't, if you look at the literature, you can find many complex stories, theory, but reading those things is really challenging for regular technical people, unless you are a mathematician. But
I just wanted to mention.
Okay, go ahead, Mahmoud.
I just wanted to mention that, like, looking at the numbers of your deployment, I mean, obviously you have a very long history of Trino, but also the numbers of like how large your cluster is and stuff like that is really amazing. Like there is a lot of queries hitting you. It must be like amazing to see the range of different queries are firing. Like when you're saying 20,000 queries per day in 2015, and now the numbers are like ridiculous. Like
we have large clusters in different continents, whether in US, in Europe, in Asia. So
what's the range of these queries that are coming in? Like do most of these queries get produced by some BI tool and are very simple, or are they very complex queries with like, I don't know, table functions or whatever?
Mostly for processing behavior or analyzing activity logs from our customers' data. So mostly ETL. Sometimes analytic queries are running ad hoc manner, but mostly 90% of queries are for batch processing, cleaning up, cleansing, so that marketers can get insight from the data.
So a lot of those queries will be like carefully crafted, and that's really amazing.
We also have a workflow system to periodically scheduled queries.
Cool. Well, thank you again very much for this presentation. We will make the slides and everything available, and people can contact and find you on Slack, obviously.
Thank you.